figure shows a copper rod, which is placed on a pair of copper rails between the poles of the two magnets. Please click the switch to observe. When the switch is on, we can observe that the copper rod moves to the right. We can deduce that the current-carrying conductor experiences a force when placed in a magnetic field. There is an interaction between the magnetic field of the current-carrying copper rod and the magnetic field of the permanent magnet. This will lead to a force being experienced by the conductor. This force is at right angles to the other two directions, the current and the magnetic field of the permanent magnet. When the direction of the current is reversed, the direction of the force exerted on the copper rod is also reversed. We can deduce the direction of the force on the current-carrying wire by means of Fleming's left-hand rule. The thumb, the forefinger, and the second finger on the left hand are held so that they are at right angles to each other. Point the forefinger in the direction of the magnetic field, north to south pole, and the second finger in the direction of the current. The direction of the motion of the wire is then pointed by the thumb. The letter F in the forefinger represents the direction of the field. The letter C in the second finger represents the direction of current. The letter M in the thumb represents the motion or force. If the forefinger points in the direction of the magnetic field, and the second finger the direction of the current in the wire, then the thumb will point in the direction of the force on the conductor. To obtain a maximum motion, the direction of the current must be perpendicular to the direction of the magnetic field. If the direction of the current and the direction of the magnetic field are parallel, there will be no force exerted on the wire. Fleming's left-hand rule only helps us predict the direction of motion, or in other words, the direction of force exerted on the wire. We can explain the origin of the force by examining the combined magnetic field of the wire and the magnet. Figure A shows the magnetic field of the magnet and the magnetic field of the current-carrying wire separately. Figure B shows the combined magnetic field when the wire is placed between the poles of the magnet. We can see that there is a stronger field on one side of the wire at A. At B, the magnetic field is weaker. A force will then act on the wire in the direction as shown in Figure B. This type of unbalanced magnetic field is called a catapult field. Click on the wire to see what happens when the direction of current is reversed. We observe that the direction of the force depends on the direction of the current. Forces between two parallel current-carrying wires. The figure shows how we can demonstrate the forces between two parallel strips of aluminium if currents flow in them. If currents pass along two parallel wires, each wire will set up a magnetic field, and the fields will interact with each other. If the two parallel wires have current flowing in the same direction, they will attract each other. On the other hand, if they have current flowing in opposite directions, they will repel each other.